have to film the instruction for the class that I'm taking, and so my professor will see the video, and no one else will see it. Hey, Boy Scout. You are. Okay, class. Clap twice if you can hear me. Thank you. Today we are doing an activity that delves deeper into geological time. Will somebody please take a look at everyone take a look at this activity that is at your tables. Somebody tell me, what is the approximate age of the Earth? What is the approximate age of the Earth?
500 million years.
Yeah, exactly. The Earth is approximately 4,500,000,000 years old, give or take 50 million years for standard deviation. So, a lot of stuff has happened since then. The activity today is to create a timeline that is to scale for the age of the Earth. So, somebody tell me, once again, looking at this paper, what is the scale in millions of years? Like 1 million years. How are we representing that in distance on our timeline?
1 million years.
Exactly. 1 millimeter for a million years. So, in order to understand this a little bit better, I'm going to show you guys a video. The video is 12 minutes long. It's got a lot of content in it. They cram 450 billion years into a 12-minute video. So there's a lot. But while you're watching the video, these are some of the vocab words that I want you to look for. Okay? So after the video, I'm going to ask you guys, what is stratigraphy? What does GTS stand for? GTS.
GT.
Carlos, can you take a seat, please? Andrea, what is the relative size of these time periods? What's the biggest? Epoch or eon? Or era? Or period? And then what is the Cambrian explosion? This is maybe the most important biological event ever. So pay attention to what these are. Jordy, would you please grab the lights for me?
We write that.
So you don't need to take notes. I just want you to be paying attention to those words because we're going to talk about it afterwards. And then, yeah, there's one better. You guys ready?
Not really.
Hey, Andy.
If you need to see the video better, you can move towards the side of the room.
Is that what you moving?
The tale of life on Earth has been unfolding for about 4 billion years, and we humans are just the last word on the last page of that story, at least so far. And the vast stretches of time that are covered by the history of life can be hard for us to fathom. We rack our brains trying to imagine what a few hundred years looks like, let alone billions of years. And like speaking for myself, I can't even remember what I had for breakfast this morning. So to help us really appreciate the full expanse of time, scientists have turned to the rocks. By looking at the layers beneath our feet, geologists have been able to identify and describe crucial episodes in life's history, from bursts of evolutionary diversity to disastrous extinction events. These key events of new life and sudden death frame the chapters in the story of life on Earth. And the system that we use to bind all these chapters together is the geologic timescale. First, let's talk about the history of geologic time itself. Because figuring out how to read history in rocks was not easy. For much of human history, of course, we had no idea how old the Earth was or what actually happened in deep time or what happened in what order. But in 1669, Danish scientist Nicholas Steno published the first laws of stratigraphy, the science of interpreting the strata or layers of rock in Earth's outer surface. Steno argued that the layers closer to the surface must be younger than the layers below them. So the farther down you dig, he thought, the older the fossils are that you find there. Sounds legit, right? But in Steno's day, when some people thought that fossils had literally fallen from the sky for some reason, this was a pretty revolutionary idea. Building on Steno's ideas, Italian geologist Giovanni Arduino went a step further and began naming the layers of rock. In the 1760s, Arduino studied the Italian Alps, organizing their layers based on their depth and composition. The lowest layers of metamorphic and volcanic rocks he called their primary layer. Above those were hard sedimentary rocks, which he called secondary, and the top layers of softer alluvial deposits he named tertiary and quaternary. But because rock layers don't appear in the same order all over the world, there was no way for geologists to compare rocks from one location to another. Without a way to compare strata, there could be no universal timescale. Finally, in 1819, English geologist William Smith figured out the solution to this problem. Fossils. By comparing the remains of ancient organisms from different rock formations, Smith could match their ages regardless of how far apart they were. For example, Smith realized that fossils of many early species of trilobites are found below ammonite fossils, which are in turn below certain kinds of shellfish. So any place in the world where you find these first trilobites, you know that you're looking at rock that's older than when ammonites lived. And even in the most ancient rocks that have little or no evidence of life, scientists can still look for signs of the very earliest major geologic events, like when continents first formed, and even when the Earth itself cooled and solidified. Thanks to the work of early geologists like Steno, Arduino, and Smith, modern scientists have used these and other clues to create what we now call the geologic timescale, or GTS. The GTS has been reworked many times to reflect the latest knowledge of Earth's history, and today it's organized into 5 subgroups: eons, eras, periods, epochs, and ages. Organizing time in increments like this allows us to ask questions about history on different scales. In the largest increments, like eons and eras, we can ask the biggest of big-picture questions, like, was there life on Earth at this time? If there was, what did it look like? Did it live in the water or on land? This is the kind of top-level view we're going to take today. But the smaller increments of time, like periods and epochs, help us take a tighter focus and ask more specific questions. Like, what was the climate like during this window of a few million years? And how did life around the world adapt to it? We'll be talking about those in more detail in future episodes when we talk about each era, period by period. Okay, so let's get the biggest of big picture views of Earth's history right now by taking a tour of all the eons and eras in the GTS. Eons are the largest slices of time, ranging from 500 million to nearly 2 billion years long, and the earliest eon is known as the Hadean. It begins with the very formation of Earth itself, around 4.6 billion years ago, and ends 4 billion years ago. And this is the only eon that doesn't have any fossils, because back then, the world was just hell. Named after the Greek underworld Hades, the Hadean lived up to its name. The planet was racked by volcanic activity, cosmic bombardments, raging storms, and temperatures that were at times hot enough to melt rock. But even in this searing wasteland, life may have been able to form. While no fossils have been found from this eon, small amounts of organic carbon have been discovered in Hadean rocks that some experts think is evidence of the earliest life. These first organisms were tiny and single-celled, but they were eventually able to shape the future of the entire planet. So their appearance is the one major benchmark of this eon. The Hadean is what...
Do you guys know what single-celled organisms are? Like, have you guys heard that before?
Organisms are stuff that is inside your organ.
Wait.
Like, are we single-celled or multi-celled?
Multi-celled.
We're multi-celled, right?
It's
So what's an
plant?
example of like a single-celled organism? Huh?
A plant?
A plant is a multi-celled organism.
I think it's
Organisms are stuff in your
Virus.
organs.
and the certain types of
Amoeba, yeah. So an amoeba is like a eukaryotic single-celled organism. There's also bacteria,
Yeah, see, that's what
yeast, plankton.
Oh, really?
Okay, so he's talking about the moment where single-celled organisms started to connect together and become multicellular. And we're gonna look at that in our timelines today. There's a big gap where the only life is single-celled.
I feel like I've done this before.
Okay.
Well, I did this like
brought to an end by the cooling of the crust of the Earth, setting the stage for the continents to eventually form. And this cooling marked the beginning of the next phase, the Archean eon, which ran from 4 billion to 2.5 billion years ago. Named from the Greek word for origin, the Archean was once thought to be when the first signs of life appeared. But at the very least, it's fair to say it's the first time that life flourished, forming mats of microbes in the primordial seas. The fossils of these microbes left behind are called stromatolites, or sometimes stromatoliths, and the very oldest of them, like those found in Western Australia, date from the Archean. During this time, the atmosphere was mostly carbon dioxide, but the appearance of cyanobacteria was about to change all that. Then, 2.5 billion years ago, the Archean gave way to the Proterozoic eon, meaning earlier life. And around this time, photosynthetic bacteria, along with some multicellular forms of life, spewed tons of oxygen into the atmosphere. This probably wiped out most of the anaerobic life on Earth, but cleared the path for crucial new organisms, including the ancestral eukaryotes, whose cells each had a nucleus and organelles wrapped up in membranes. Eukaryotes developed into the first really big, complex, and sometimes kind of weird forms of life, such as their fund-like Carnea and the plate-shaped Dickinsonia. These new, larger organisms quickly diversified, and by 541 million years ago, we were at the doorstep of the next and current eon, the Phanerozoic. Its name means visible life, and the Phanerozoic was when life really became obvious. This is the eon that's home to trees, dinosaurs, newts, aardvarks, us humans, basically life as we know it. Whew! How are you holding up? You doing okay? We've covered about 3.5 billion years already. Just got another 500 million to go, and then we're home free. Okay, now from here, it's best to explore the Phanerozoic eon through its eras, the next level down in the divisions of time. This will let us explore more recent history in greater detail. The first era of our current eon is the Paleozoic era, which began 541 million years ago. This chapter was defined by the diversification of visible life, and it started with a bang, actually an explosion, the Cambrian explosion. This rapid growth in diversity and complexity in the world's oceans is such a huge deal in the history of life that all the eons that came before it, the Hadean, the Archean, the Proterozoic, they're all collectively known as the Precambrian. At the start of the Paleozoic, over about 25 million years, the fossil record suddenly reveals the appearance of complex animals with mineralized remains. You know, hard parts, shells, exoskeletons, that kind of thing. And the very first of these new animals to become truly widespread were the trilobites. They were so common all over the world that they've been used as index fossils for the Paleozoic era for centuries, ever since the days of William Smith. But the trilobites soon had competition. Fish developed teeth and jaws and came to dominate the seas, including the first sharks and armored giants known as placoderms. Meanwhile, the land, which had been barren since the formation of continents back in the Archean, was finally being populated, first by plants and then by arthropods. By 370 million years ago, entire ecosystems had developed on primeval continents. Soon after, the earliest amphibians evolved and hauled themselves out of the water, leaving the first vertebrate footprints in the mud. 299 million years ago, the supercontinent of Pangaea had formed, with an enormous desert at its center. This desert was quickly populated by the ancestors of what would eventually become reptiles and mammals, which could thrive in dry conditions, unlike amphibians. But this time of incredible growth couldn't last forever, and instead, the Paleozoic era ended in cataclysm. 252 million years ago, 70% of land vertebrates and 96% of marine species disappeared from the fossil record, including survivors of previous extinctions, like our friends the trilobites. I still miss those guys. The event known as the Great Dying was the most severe extinction in our planet's history, but its exact cause is still unclear. A possible meteorite impact off the coast of South America might be one clue, and in Siberia, layers of basalt show that massive volcanic eruptions covered large swaths of Pangaea in lava. Both of these incidents coincided with the end of the Paleozoic, and it seems more than likely that the extinction had many causes. In any case, the Paleozoic may have begun as a chapter defined by an explosion of life, but it ended in nearly absolute death. It took millions of years for life to recover, but when it did, a new world, the Mesozoic era, had arrived. This is often called the Age of Reptiles, and with good reason. Right from the start of the Mesozoic, reptiles were incredibly successful. This is when they took some of their most famous forms, like dinosaurs, pterosaurs, and a variety of marine species. In fact, all of the non-avian dinosaurs lived only in the Mesozoic, so they remain one of the best index fossils of this era. And many modern groups of organisms also evolved in the shadows of the reptiles, like mammals, frogs, bees, and flowering plants. But the Mesozoic era came to an end 66 million years ago, with yet another episode of devastation. This time known as the Cretaceous-Paleogene, or KPG, extinction event. Like all mass die-offs, the KPG had many causes, but probably the biggest of them was a giant asteroid that struck the Earth, sending enormous amounts of ash into the atmosphere, blocking out sunlight, and creating a vicious cold snap across the planet. Without the sun's energy, entire plant communities died, and the animals that relied on those plants perished with them. Evidence of this impact can be found in the layer of iridium in rocks dating to the end of the Mesozoic. Iridium is an element that's rare on Earth, but very common in asteroids and comets. And a giant impact crater in the Gulf of Mexico, whose age matches the date of this extinction, has become the smoking gun for the asteroid hypothesis. The victims of the KPG extinction were some of the biggest reptiles of the land, sea, and sky, including all of what we now call the non-avian dinosaurs. Birds, of course, survived the cataclysm, making them the last surviving lineage of the dinosaurs. Okay, we have 66 million years to go, and that's the last major extinction event that we have to talk about. I thought you might want to freshen up, so I bought these pre-moistened towelettes. Just going to... You have some iridium hit on this side, on your forehead, other side. With all the great reptiles gone, the smaller animals that remained were able to eke out a living in the next era, the Cenozoic. This is our era, in more ways than one. It's the era that we're in today, and it also marks the rise of the mammals. Soon after the KPG extinction, the climate warmed, and jungles stretched across the planet. Mammals quickly recovered in this hothouse world, and by 40 million years ago, most of the mammal groups that we recognize had come about, like whales, bats, rodents, and primates. But starting around 34 million years ago, the climate began to shift again. This time, ice caps started to grow at the poles, taking up much of the planet's water. And these drier conditions created a new habitat, the grassland, where ancestral horses and antelope were hunted by the first cats and dogs. It was also in these grassy plains, 7 million years ago, that a species of ape called Sahelanthropus became the first known primate to walk upright. 2.6 million years ago, the ice caps expanded even more, and the Earth entered a glacial period. This is the one you hear referred to as the Ice Age. Over the course of these last several million years, most modern life forms that we know about developed and thrived, alongside giants like mammoths, ground sloths, and saber-toothed cats. Once again, though, this era of diversity came to a morbid end. Starting around 15,000 years ago, the climate began to warm up, and over the next few thousand years, many of the giant fauna went extinct. By 11,700 years ago, the last major glaciation was over, and modern humans inhabited nearly all the corners of the globe. But how big a role we played in the extinction of the so-called Ice Age megafauna is hotly debated. Regardless, there's no escaping the fact that our species has shaped the Earth to its will since then. Like cyanobacteria and the dinosaurs before us, we've had a huge impact on habitats, other organisms, and the biosphere itself. And as we've learned today, it's the most dominant forms of life that define each phase of deep time. So even though our time on this planet amounts to the last word on the last page of the story of life, we are the authors of the next chapter. One day the epoch of humans may be detected by the marks we make on the land, the traces of our cities and farms, and our very bodies will be the index fossils of this time. No matter how our chapter ends, we get to be characters in a truly amazing story. Thanks for joining me on this epic...
Okay, lights.
Cameras.
Action!
Ah!
So, class,
Monday.
stratigraphy. What is it? Yeah, exactly.
Study of the strata.
The study of Earth's strata. The strata are the layers of rocks. So the oldest are at the bottom, the youngest are, and they progressively get younger as you go up. Geological time scale, that's right.
Are just parts of it, of the GPS. Eons or the
Which ones are the biggest?
Eons, then it goes to eras, then it goes to periods, then it goes to whatever that is.
Epochs.
How do we know who coaches? And then
It goes eons to eras to periods to two bucks.
and the Cambrian would be the beginning of the epochs we know already.
Exactly, exactly. So they actually divide geological time into, clap twice if you can hear me. They divide geological time into the Precambrian and the Postcambrian. Question?
How do we know how that sounds like that?
It's all speculation. We don't know how they sounded like.
So what if they sound like a chicken?
Well, they sound like
Likely.
a chicken.
Well, they are.
Well, typically, if you have a bigger animal, it's going to have thicker vocal cords than a very, very small bird, right? Okay, so the task for today is to create a geological timescale. These guidelines are around the classroom. The supplies you need are receipt paper. Okay, I've got rolls of it in the back right there. Meter sticks. There's meter sticks scattered around. There's also a big box of meter sticks right there in the back of the classroom. You need to measure out at least 4.5 meters. The reason for that is because the Earth is 4.5 billion years old, approximately. And so,
One's broken.
how long is a million years on this time scale?
1 millimeter.
1 millimeter. So, if 1 millimeter is a million years, then 4.5 billion years is going to be 4.5 meters. So let's say that let's say that this is your paper. You're gonna leave a little bit of tail on the ends. Start here. Let's say this is gonna be present day.
Look, this broken is dangerous.
This is the origin of the earth. You're gonna draw a timeline. Okay? On this timeline, you're gonna put all of the events from this table. So, you start by putting all the events from this table, start from 0, just like Drake. Start it from the bottom, now we're here.
No. No.
Go to the back table once you're done with all those. This is where all of the epochs and eras are.
So we just have to copy and paste that on the paper.
You don't even copy and paste it, you can just write it out with a pencil. I would recommend that you make them really nice and pretty and creative and draw pictures and use markers and all that, because they're gonna be posted in the hallway. I would love it if I had something really nice to post in the hallway.
On purpose, like really bad.
I would say that you should reevaluate your priorities in life. Okay, what questions do you all have for me?
Now, this is broken and it's dangerous.
No?
You
No.
can stab somebody with this. What do you mean, no?
You should not give it
Do I have any real questions? Okay.
I'm still confused, so.
Okay, I will address that individually. Y'all are good? How about you? Good? Got it? 2 in the back? So the groups are gonna be, you 3 are one group, you 4 are a group.
Okay, not yet.
Actually, Jessica, go with Frida and Fernanda. Carlos, Wendy, Ali, and Hector, group.
You okay?
Gio, Andrea, Brian, Jordy. Y'all are a group of 4. Okay. If, class, clap twice if you can hear me.
Clap, clap.
Clap twice if you can hear me. If the groups aren't working out, I'm gonna make them smaller and it will turn into an individual
Oh,
project.
no.
Okay? So,
Era para mis pies.
be efficient,
Get it.
be straightforward, ask questions if you need help. All right. Once again, receipt paper is there in the back of the classroom. Get an appropriate size piece. Meter sticks are over there.
Hey, son nosotros 4.
Get to work, y'all.
Yeah.
No. I got her paper.
I know you just so very
How can I wear muscle shirts?
And like it's probably can see like right there.
My nose and my hands are
How would you feel if I did? I want you talking to Leo. I want you talking to Leo. You're supposed to be my only best friend. Wow. That is bad. I mean, I don't think it's fair.